Alright guys, so in today's video we're going to be looking at the first lesson in Unit 7, is looking at molecular compounds and covalent bonding. So as you will go through watching this video, you can either take notes in your notebook as you go along with the information on the slides, just as you traditionally would in the classroom, or what you can do is download the guided note sheet that's posted on Canvas, open up a Notability, and write directly onto those slides. So for today's class, just make sure we are following the information. All you guys have to do to get the participation points from the classwork for today is submit either the photos of those notes you take in your notebook or upload the document of the guided note sheet after you have completed it. So getting into the information, again, we're looking at molecular compounds and covalent bonding in this unit. They're going to begin in chemistry. So over the past 2 days, you guys have, through the reading assignment and the Edpuzzle video, have looked at information relating the terms molecules, covalent bonds, molecular compounds with one another. So we're going to just take a moment, summarize that information, make sure we're all on the same page here as we move forward. So the first thing we're going to do is break down this definition of what a molecule is. So we'll begin by saying a molecule is a neutral group of non-metal atoms joined together by covalent bonds. So we'll break it down in a second here. The first thing we're going to look at is this idea we're dealing with non-metal atoms. So we think back to what we covered last unit with our ionic compounds. Again, for ionic compounds, we had to have a metal bonded with a non-metal. As we move into these molecular compounds, these molecules, we're only going to be focusing in on non-metals. So it can be made of one non-metal, two, more than that, but we will never have any metals in these molecules. The second thing we're going to focus on is this idea that we have this neutral compound here. So a molecule has to be neutral. So for something to be neutral, again, we're going to have a charge of 0. So this is actually going to be in a way similar to looking at the ionic compounds we had before. Even though each ion had either a positive or negative charge, ionic compounds as a whole unit had a charge of 0. They were overall neutral. So just as ionic bonds were held together by ionic bonds, our molecules are going to be held together by our covalent bonds. The big distinction here is that our covalent bond is going to hold these atoms together through the sharing of electrons between our atoms. So when we looked at ionic compounds, again, we had a metal gave up one of its electrons, and that electron went to the non-metal. Here what we have is electrons are shared between two atoms. So let's say we take carbon dioxide is a molecule, carbon, oxygen. Those carbon and oxygen atoms are going to share electrons between the two of them. One very common category or type of molecule is what we're going to refer to as a diatomic molecule. And these diatomic molecules have to contain only 2 atoms. So they're the simplest molecule we can have. We said up top here that a molecule had to be a group of atoms. We had to have more than one. So the simplest molecule we'll have is a diatomic molecule with just 2 atoms in it. So some of our very common gases occur naturally as diatomic molecules. You're going to take the oxygen we breathe in the atmosphere and the air around us. We think of when we say we breathe in oxygen gas, what we're really doing is breathing in the O2 molecule of 2 oxygen bonded together as they share electrons between the two. Now, moving into some more complex molecules, are ones that have more than just one type of element. And this is what we're going to do is build into this idea of a molecular compound. So earlier we said that a compound, big idea for it was that anything, any substance that was made up of more than one element So if our molecule is made up of more than one element, this is going to result in a molecular compound. So some very common things we experience in our daily lives, examples of molecular compounds, We have carbon dioxide that we breathe out of our lungs. We have nitrous oxide. We have glucose, sugar, so what animals or plants produce through photosynthesis, what animals consume and use up through cellular respiration that you guys touched upon last year in biology. So just as we were able to write chemical formulas for ionic compounds, we're going to be doing the same thing in writing chemical formulas for molecular compounds. We call these chemical formulas for molecular compounds our molecular formulas. So again, the big thing we're going to focus in on these molecular formulas, the three examples listed above here were all examples of them, is that these molecular formulas are going to tell us how many atoms we have of each element that are in the compound. So while they tell us in carbon dioxide that we have 1 carbon for every 2 oxygens, it really doesn't actually tell us anything about the structure of what that molecule looks like. It tells us what's in it, but not how those different atoms are arranged compared to each other. So when we want to think about these molecular formulas, we're going to compare them to the ionic compounds we studied before. So whereas the ionic compounds told us this simplest whole number ratio between our different ions, our molecular formulas are going to actually tell us how many atoms we have in a molecule. So we're going to have many cases where we aren't going to have a lowest whole number ratio. What we're dealing with is just the actual amount of atoms of each element within the compound. So we think back to an example we had on the quiz for ionic compounds, where we had aluminum nitride. Many students put Al3N3 as the chemical formula for it, based off that crisscross method we covered last unit. But the issue with our ionic compounds, when we looked at them, we could say, right, a 3 and a 3, that's not the simplest ratio. So before we said that this was not simplified, so we had to simplify our aluminum nitride down into AlN. So the big thing we're going to have to focus on for this time is that we do actually not want to do this with our molecular compounds. So we don't do this with our molecular compounds. And the reason why we don't do this is that our molecular compounds tell us the actual number of atoms we need in that molecule. So when we look at the example of butane, a molecule of butane has to have 4 atoms of carbon and 10 atoms of hydrogen bonded. But these 14 different atoms are all going to be sharing electrons with each other. Big thing we have to remember is that we do not want to simplify them. So we cannot simplify butane down to C2H5. These two things are actually completely different compounds. Then the final thing we'll do for class today is look at just a quick comparison between these properties of ionic compounds versus molecular compounds. So again, you can either take these notes down in your notebook, or you can fill in the guided note sheets that I posted on Canvas. For the assignment today, you have to upload a finished copy of one or the other to Canvas. So we think about our ionic compounds. Right? The bond that held those atoms together are going to be our ionic bonds, and this involved the transfer of electrons to form these ions that can then attract each other. On the other hand, what we looked at today in the past couple of days is looking at our covalent bonds, in which electrons can be shared between various atoms. We look at the representative unit of each, right, the smallest unit we can think of. Our formula unit for ionic compounds just told us what was that lowest ratio between our ions, between the positive ion and the negative ion. What we have, though, for our molecular compounds is a molecule is actually a physical unit, that exists by itself. So as we look down to the very bottom picture of their structure, where we look at what a typical ionic compound looks like, it's going to be a whole bunch of positive and negative ions all arranged together in this 3D structure, in this crystal structure. So the formula unit again just tells us that for every 1 sodium we have to have 1 chlorine. It tells us a ratio. Whereas with our molecular compounds, when we look at just a molecule, what it's doing is it's actually telling us what a single unit is. So we look at water. Water has to be 2 hydrogens and 1 oxygen. Those 3 atoms bonded together, as seen in the picture, are going to form a single unit. We can never have a molecule of water with more than 2 hydrogen atoms or more than 1 oxygen atom. Even though in a glass of water we're going to have many millions of water molecules, they each exist as their own separate units, as we can see in the picture here. They're all going to exist separately, even though they might all be in the same container. When we think about what types of metals or what types of elements make up our ionic compounds, right, we have to have 1 metal with 1 nonmetal for our ionic compounds. Molecular compounds, we're only dealing with nonmetals. We could have a case of like one of our diatomic molecules like oxygen, where there's just a single nonmetal, or we can have something like carbon dioxide or the water shown in the picture below, where you have 2 different elements, both of which are nonmetals. Again, there really isn't much of a limit to the number of different nonmetals we can have. Something like glucose has 3 different elements in it. As we get more and more complex with our molecular compounds, we can have many different types of elements all involved with these molecular compounds. What we have is just 3 last things concerning some of the properties of ionic crystal molecular compounds. Again, when we looked at the physical state or the structure of these ionic compounds, we said that they were solid crystal structures. We can see that in this kind of 3D arrangement of our ions in this picture below. But when we look at our physical state of molecular compounds, there's a wide range that they can be. We have things that are solid, such as sugar, glucose, solid. The water picture below obviously is a liquid. The oxygen molecules that we breathe in are going to be gases. So there's no set one state that a molecular compound has to be. When we look at the melting point of ionic compounds, we said they were very high melting point. As a result, they were very stable, rigid structures, whereas our melting points of molecular compounds are going to be much lower. Lastly, we said ionic compounds were good conductors when they were dissolved. So we could take salt, put it in water, dissolve it into the ions, and that saltwater solution would conduct electricity. What we have on the other hand of our molecular compounds is they're very poor conductors. Some of them do not conduct electricity at all when they're dissolved. We refer to them as non-conductors. So when we look at these last 2 pieces of information of melting point and electrical conductivity when dissolved, they pretty much are the opposite of each other here. So as again, for today's assignment, all you have to do is submit a copy of the notes you take from this video. Again, that can either be written in your textbook or in your notebook, or it could be just uploading that guided notes file that's posted on Canvas. If there's any question about the material, please post it in that discussion thread for today's class. That way I can respond to them and your classmates can see the answers to those questions that you might have. Again, any other questions that come up, please come in contact with me either through the discussion thread or by email. I'm here to help you as you move through these next couple weeks of distance learning.